Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to the course on computer aided drug design. We have been talking about force fields, molecular mechanics, then we looked at different types of force fields, then we looked at conformational search, and then we also looked at some numerical methods for solving differential equations. So, we will continue a little bit on this conformational search because that is a big challenge. How do you know that the molecule conformation is equivalent to a minimum energy, and that is what we have been looking at in the past few classes. Okay. So, basically you may start at different places and you may end up at some minima, but this is a local minima, whereas this is the global minima. So, depending upon where you start you may end up, but your goal is to reach this global minima. So, conformational search is a big challenge. For small molecules it is okay, but for large molecules it becomes a big problem, and as you know the biological activity sometimes depends upon the conformation, whereas when it goes and binds into an active site it may have a different conformation depending upon the flexibility of the bonds and so on. So, there are different types of conformational algorithms. So, how do you know you have reached minimum energy? Okay. I mentioned that you can look at the change in energy, or you can look at the delta E by delta change in the conformation, but that could leading to a local minimum rather than global minimum. But some of the approaches that are followed to find out whether you have reached global is to start with various starting conformation. For example, I suppose I start with 1, I may end up with a minimum which is not global but local. Then I start with 2, I will go down much lower than this, then I may start with 3 which may go here, I may start with 4 which may go here. So, by starting with different conformations and then keep minimizing and then look at the minimum of this minimum, and that we call it the global minimum. Okay. That is starting with various starting conformation. You can also have systematic search, that means you change bond length, bond angle, torsion very systematically, keep on calculating the energies, but that is going to be very time consuming because when you have say 10 bonds, 20 angles and 30 torsions, imagine it will be in almost like raised to the power. Another approach is called simulated annealing, that means you heat the molecule to a higher temperature, because of the energy the molecule has, it takes a lot of conformations, and hopefully when you minimize those conformations it will lead to a global minimum. And then another approach is molecular dynamics, by which we can also get conformation. We will look at some of them a little bit in more detail. So, the main challenge here is to reach the global minimum, not end up with local minimum, that is the main challenge. Okay. For example, if you look at butane, okay, butane as you know is a C4, okay. And it can take this type of conformation or this type of conformation. That means here the bond is sticking out of the paper, whereas here the bond is going inside the paper. But then there is only small change in the energy, 0.9 kilocalories. Okay. So, you cannot say all the 100% will be in the minimum energy conformation, you will have ratio because the change is only one little. Look at substituted cyclohexanes. This is substituted cyclohexane, okay, and the cyclohexane can, as you know, can take chair conform or boat and all that, right. Substituents are either equatorial or they are axial. Okay. So, they can be like this or like this. Look at cis decalin, okay, decalin as name goes 10. Okay. So, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So, you have one closed ring, another closed ring. So, it can take 2 different conformations, okay, like this and like this. So, if you look at cyclohexanes, we all have studied it can take chair form or boat form and so on, right. Okay. If you look at monosubstituted cyclohexanes, the ring flipping is of the order of 104 to 105 inversions per second. Okay. So, it can change quickly, and this is the free energy on the y axis. So, this can be half chair, this is full chair, again half chair, this is again chair. So, it can be flipping this way and that way. This is taken from this particular reference. So, as I mentioned before, the change in the energy is only 0.9 kilocalories. So, it is not a big deal actually. Okay. So, it is not a big deal for us. As I had mentioned before, we can look at the Marvin sketch, and as we can also get the, for example, this is cyclohexane, and this is a substituted cyclohexane. Okay. This is a substituted cyclohexane. So, we can say structure clean in 3D. Okay. So, we have the 3D version of this, and as you know, okay. So, this is for this, and we can look at it like this. Okay. So, this is not the minimum energy conformation. So, we can look at so Marvin sketch, as you know here. We can view it in different forms. I had mentioned it before. So, it can be a wireframe type of form. Okay. Ball and stick. Okay. Now, we can look at some calculations, we can look at conformations, different conformers we can say. Okay. So, I want to look at 10 conformers here. Look at this. Okay. So, it is giving you different conformations of this substituted cyclohexane. So, this is 9.75. So, this is very different. Okay. So, forget about this. This is 1.42. This is substituted. This is 8.05. Okay. Look at this conformation. Okay. As you can see, this is nice looking chair. So, it gives you different conformations of the molecule. Look at this. This is a 27 point. Okay. So, definitely very high energy, whereas look at this conformation. Okay, 2.09. Okay. This is a 7.42 conformation. This is 0.75, still lower than this. Okay, so you get a beautiful picture here on this. So, a lot of conformers with different energy. Okay. So, if you want, we can calculate with the MF. Okay, MMFF energy optimization limit is normal. So, we can give a strict optimization also. So, by doing that we okay. So, we can see this this particular conformation is quite low energy wise, energetically. Okay, this gives you the lowest energy, which is 0.7 kilocalories, and this particular gives you quite a high energy, 8.3 kilocalories. Okay, so as you can see the distortion whereas the distortion here is much lower. Okay, distortion is much higher. Okay, whereas here you can see it nicely sits in. Okay, the carbon sitting here, that is why the energy is very low, 0.7 kilocalories. Okay. So, you can see from this software also we can get different conformations of the molecule. Okay, can get different conformations of the molecule here. Okay, so we can go into conformation, conformers. So, we see 13 kilocals, 13.5, 13. So, some of them are good, 14. So, you get different conformations, but most of them are almost same, very little differences in these conformations because the software tries to minimize the energy. Okay. So, there is a very important the conformations are populated according to Boltzmann distribution such that the relative populations are proportional to E minus G by RT. Okay. So, it is not that you will always find one the minimum energy conformation. For example, butane you will find both anti and gauche in the ratio of 70-30. Okay. We will see anti and gauche in the ratio of 70-30 because their distribution will be based on E minus G by RT. In many cases the lowest energy conformation is not the conformation that reacts. Okay. So, lowest energy. So, the biological reaction need not be the lowest energy, and there is a rule called Curtin-Hammett principle. We will look at that. So, important to know all the conformations that lie within a few kilocalories like I showed you in some of these examples. So, just do not go and stop with minimum energy. We will look at conformations with the plus or minus 2 kilocals. Look at all those conformations because as you know the conformations are populated according to this particular distribution. Okay. So, if the energy is higher you will have less of it, but still you will find some. If energy is lower you will find more of it, like for example butane you will not find only the minimum energy, but you will find the other one also, but the ratios will be different. Now, what is this Curtin-Hammett principle? What it says is the reaction that has a pair of reactive intermediates or reactants that interconvert rapidly. So, if you have say AB, two different conformations, they interconvert between those two conformations very fast because the energies are that is conformational isomers, the energies are not very different high, each going irreversibly to a different product. So, they quickly shift from one conformation to another, but then they go into the product. So, the product ratio will depend both on the difference in energy between the two conformers and the energy barriers from each of the rapidly equilibrating isomers. Okay. So, if I have a particular ratio, it is not that I will get the same ratio as the product, but it will also depend on the difference in energy between the two transition states. So, the product distribution will not necessarily reflect the equilibrium distribution of the two intermediates, remember that. So, two conformers interconvert rapidly, there is a very small difference in their energy, and then they go into product that which is irreversible. Because they can interconvert rapidly in equilibrium, the product distribution will be based on this difference in energy between the two rate limiting transition states. Okay. So, one of the approaches is like I said, systematic search method. There is a systematic generation of conformations. So, thereby you explore the conformational space through assigning discrete values to torsion angles, rotatable bonds and all that. But then it is not so easy. Important bonds of the molecule are rotated by random amounts to generate a new structure, then the resulting structure is minimized. For example, butane has only one key band that can rotate, so it can give 3 conformers. Pentane has 2 key bonds. Pentane means C5, okay, 1, 2, 3, 4, 5 pentane. So, pentane has so pentane, how many key bonds has it? Pentane has 2 key bonds, okay. So, this bond and this bond, pentane has 2 key bonds, whereas if you look at butane has only 1 key bond, okay. Butane for example, this is the only 1 key bond for butane which can rotate. Pentane has this bond and this bond, 2 key bonds which can rotate. So, in the case of pentane you can have 9 conformations. Hexane has 3 key bonds, okay. Hexane for example, let us look at hexane. Three, 4, 5, 6. Okay, so hexane has 3 key bonds 1, 2, 3. So, we will have 27 conformers. Tridecane, that means C13, decane is 10, tridecane C13 will give you 59,049 conformers. So, you see it is not so easy, there are so many rotatable bonds as your carbon number increases. So, you may have to look at so many conformations. Okay, as you can see from butane to pentane to hexane to tridecane, the number of conformers increase rapidly. Then you have random search, that is another approach. It can move from one region of the space to completely unconnected new region in a single step. So, you randomly change things, you may change that Cartesian coordinates, okay. Cartesian coordinates means x, y, z, or torsion angles of rotatable bonds. You go another approach that is called Monte Carlo search, this is based on statistical mechanics. Then we have the genetic algorithm, these are called a class GA, a class of optimization method that are based on Darwinian evolution. So, you large scale optimization algorithm mimicking a biological evolution in a randomly generated population. So, you look at number of conformations from this population, okay. Then you look at those population, adaptation is calculated and a new population is created in accordance to operators, crossover, mutation. Okay, so, you keep on, you look at a set of conformations, you take those which look good, then eliminate the ones which do not look good. So, that is like almost like evolution and then proceed, okay. That is what is called genetic. There are various variations to genetic algorithm also. So, okay, once we do the conformation, we need to know whether the molecule has attained its what is predicted and realities. As I had mentioned before, X-ray is a very good technique, it gives you the coordinates of the molecule. So, we can cross check whether conformation matches. Electron diffraction, Raman spectroscopy, ultraviolet spectroscopy, IR, NMR, microwave, photoelectron, supersonic molecular jet spectroscopy, optical rotatory dispersion, okay, quantum mechanics, so many, and quantum mechanics is a theoretical approach. So, so many experimental approaches that can give you an idea about the location of the functional groups, location of the carbons, location of various atoms, and then you cross check your predictions with the reality. Okay. So many different methods, experimental methods, and of course this is a quantum mechanics, this is a theoretical method to cross check whether you have reached the minimum energy conformation. Okay, as I had mentioned that many cases minimum energy conformation is not the biologically active conformation, and that might not be the real conformation when molecule goes and binds to the active site. So you always try to look at conformations which are closer to minimum energy as well. Okay. Another approach which you can do is using molecular dynamics simulation. So what do you do in molecular dynamics? We need to basically you are solving this equation. This is Newton's second law, d square x I dt square is equal to force divided by m. Okay. Okay. Force is equal to ma, you must have studied long time back. This is equal to acceleration. So if you integrate this equation, you can get the coordinates, new coordinates starting from one set of coordinates at certain time point, given a force and given a mass. So you get successive conformations of the system as a function of time by solving this particular equation. Okay. Okay. So so it gives a trajectory that specifies how the position and velocity of the particle in the system vary with time. Okay. As you solve, you know the coordinates xi at the time ti. So when you do ti plus delta t, you will find a new xi plus delta t and so on actually. So basically you are solving that Newton's law of motion. Three types of problems. No force acts on each particle between collisions. Okay. The particle experiences a constant force between collisions, that is charged particle moving in an uniform electric field. So there is an uniform electric field, so they uniformly feel a force, whereas the first one there is no force acting until they collide. Force on the particle depends on its position related to the other particles. Okay. So there could be attractions, repulsions and so on. So these are different types of things that can happen when you do a molecular dynamics. So what do you do? As I said, integration is broken down into many small stages, each separated in time by a fixed time delta t. Basically it is a numerical integration. The total force on each particle in the configuration at time t is calculated as a vector, sum of its interactions with other particles. Okay. Then from the force we can determine the accelerations, then we get the positions and velocities at t plus delta t. That is what molecular dynamics does actually. The force is assumed to be constant during this time step. You cannot assume that during this time step delta t the force changes, that complicates the whole issue actually. Then you determine the force of the particle in the new position. Okay, so you again calculate t plus 2 delta t positions at 2 delta t and so on, velocities also you calculate at t plus 2 delta t. In that way you keep on going forward. So molecular dynamics is basically a forward starting from at t is equal to t0, you run the simulation for certain picoseconds and then calculate the new set of coordinates of the molecule. So all the algorithms assume that the position and dynamic properties, that is velocities, acceleration etc., can be approximated at Taylor series. Okay, because as I had mentioned, solving differential equation is basically a Taylor series type of expansion. Okay. So once you bring all the molecules together, we sort of equilibrate these molecules so that they are not overlapping, atoms do not overlap, they are sufficiently at for their distance and so on actually. Okay. So that is what we try to do when we do the molecular dynamics. So these are the different types of techniques that are available for predicting or for telling whether you have reached the minimum energy conformation of the molecule. Okay. So systematic search method. Okay. Then of course problem becomes very difficult as the number of rotatable bonds become more. Random search, you randomly go here there and then try to see the I mean here there means you get different conformation and see how the energy looks like. Monte Carlo method based on statistical mechanics, genetic algorithm method is based on selecting those conformations which are favorable, rejecting, and then coming up with a new set of conformation, almost like evolution, coming up with a new set of conformation based on the population of old set of conformation. Then of course we have the molecular dynamics approach, where we start with one set of one conformation at time equal to T0, and then you solve the Newton's second law. Force is equal to ma, A is the acceleration, that is d square x by dt square, where x is the coordinates of each of the atom, and you move from one time step T0 to T0 plus delta T, T0 plus 2 delta T, and so on, and then calculate the new positions by solving this equation. So the atoms move as a function of time, so there could be a constant force acting on them, for example in a constant electric field if the atoms are charged, or there might not be any force acting when they are not colliding. When they are colliding, of course, because of the collision there are some forces. So you keep doing the numerical solving this differential equation from one time point to another time point and so on. So when you start going up to large time steps, the molecule would have taken different conformations which are very novel, and then you can look at those conformations and see whether you from there minimize the energy and then see whether it has reached the minimum energy conformation. So these are different approaches by which you can try to arrive at the minimum energy conformation. And as I said, the minimum energy conformation need not be the conformation in which the biological system may be reacting, and sometimes like I showed many examples, the conformation between the minimum most energy system and those closer to minimum energy might not be much. So you will find molecules with different conformation based on that Boltzmann's equation e power minus g by RT. Okay, so the distributions will be in that order. So it is always good to look at the conformations of molecule which are slightly above the minimum energy conformation also. Okay. So with that we complete the topic of molecular mechanics, force fields. So because this is the most important, we had spent a lot of time on this, and as I showed you free software which can get you to draw structures of organic molecules, or we can import structures from for example Swiss ADME or even from zinc, and then we can minimize energy. It's got only one or two couple of force fields, but if you look at other softwares you may find more force fields. So we can look at conformations, and then after that we can do a lot of property calculations. Okay. So with that we will stop, and in the next class we will talk about quantum mechanics. Okay. Thank you very much for your time.